Signal.
Okay, so we can begin. Thank you very much to be all there. So we are attending to your PhD about stellar streams, model active in cosmic archaeology, and I will describe the content of the jury. George Penarubia from Edinburgh, Annalisa Marie from Edinburgh also, are two referees, and there are three examiners. Christian Bolly from Strasbourg, here, Eugène Vassiliev, also from Surrey, and Rafaela from Roma, and the two, Paula and Marco Maturi for the supervisor. So, Salvatore, you have 45 minutes and then we'll ask questions.
Okay, thank you. All right, we started going a little bit. Thank you so much for coming. I think I could say this 1,000 times. I'll probably thank you again at the end. And I will share with you my work the best I can, discussing the dissolution of globular clusters due to galactic tidal forces and how they create stellar streams, and particularly in the Milky Way. And this is a little animation of that, and I'll break it down. So first, I'll start with the background context, beginning with just one globular cluster. Star clusters, they have hundreds of thousands to millions of stars inside of them, and you can consider them to be stars that were all born at the same time, and they also have about the same chemical composition. The interesting part about them. Next, if you want to consider the distribution of globular clusters in the Milky Way, we can start looking at this graph on over here. And I would like to start out first by pointing out the sun. And you can note that if you look towards the center of the galaxy from the sun's position, you can see many globular clusters along the line of sight. However, once you get past the other side of the galaxy, there's less. And this also goes to show maybe some observational challenges or improvements that have come over the past years. For instance, this picture is from the Harris catalog. I believe it's over 10 years old. And the counts are 111 globular clusters. At the onset of this work, we had cataloged with complete data about 160 globular clusters. And now we're getting towards 200, where maybe the remaining 40 are still either candidates or confirmed detections, but perhaps not all their parameters are fully flushed out. And all of this is thanks to the Gaia mission, which has been the mission creating the data that makes the data products that I use for describing the globular clusters. And it was launched in 2013, and it was just deactivated a couple months ago. But there are still petabytes and petabytes of data that are going to be continually processed over the coming years, and there should be 2 more major Gaia data releases by 2030. All right. Now I want to talk a little bit about the different timescales involved in this problem. You can start by considering you have a star orbiting around the globular cluster, and you also have the whole cluster orbiting around the galaxy. Like many astrophysical problems, there are different timescales that you need to consider. So maybe a star orbiting around the cluster could take a couple million years, 5 million years, while the whole cluster going around the galaxy may take 300 million years. And I want to show that in this little animation here. Here I have the frame rate set to the orbital time of the stars in the cluster. But once I zoom out, you can now see the cluster compared to the size of the galaxy, and I accelerate the frame rate in the animation to now put it on a time scale comparable to the orbit of the cluster. You see the stars escape, they redistribute themselves along the stream, or along the orbit, creating the stellar stream, and this is the useful part of stellar streams, which is that they trace the orbits, so it gives you more information about the galactic gravitational field than you would otherwise have just from 1 point information worth of position and velocity. Regarding the stellar streams in the Milky Way, I would like to start with this plot on the, I confused the right and the left because we're looking at different directions. On the left, it's the number of stream discoveries versus the year. It starts in 1996, which is the year I was born, so it's not a coincidence. And you can see that there's a large spike in the number of detections when Gaia entered the field. And this is also thanks to the group in Strasbourg, partially. They created this algorithm. Oh, sorry, there was a question. Yeah, okay, gotcha. Sorry, yeah, how many arguments? They created this algorithm, Stream Finder. It finds streams agnostically in the data by searching for co-moving groups of stars, where prior to this, you would do targeted searches. You would look at a globular cluster, see the stars inside of it, find similar stars outside of it, and make your detections this way. So even though we have about 120 streams that are currently observed, and about 160 globular clusters that have been characterized, only 20 have been associated with one another. So this prompts us to ask some open questions. Since we expect tidal stripping, stellar stream formation to occur for all globular clusters, how many cluster streams should we expect to find in the galaxy? How many of them have not yet been discovered? And then once you have these streams, another set of questions is how sensitive are they to the galaxy's gravitational field in particular? You can start with a basic cylindrically symmetric model for the mass distribution in the galaxy, but you can start complexifying it and making it more realistic. You could add a rotating stellar bar that could influence the streams. We've been quite interested in that in this project. And then also you can add other characteristics to make the model for the galaxy's gravitational field non-smooth. How do all of these factors influence the stellar streams? Then these are some of the open questions that I wanted to get towards. And before getting to that, I would like to discuss the physical mechanism for creating the stellar streams. So some background information. We can start with how I model the problem. It's the restricted three-body problem. If you wanted to do an appropriate or more accurate treatment of a globular cluster, you would consider all of the pairwise forces of the bodies within the cluster. And if you have 1 million stars, that would be 1 million squared forces you compute. We're on the order of 10 to the 12. And so this is possible. People do this, some people in this room. And but it's still computationally expensive, particularly when you have a large parameter space to explore. So you can simplify this by instead only considering 3 interactions, and you order it hierarchically. So you have the primary in your system, which would be the most massive. So this is the galaxy. Then you have something representing the net globular cluster, which is the secondary. And then you have the tertiary, or just the star. And the star is subject to the cluster and the galaxy. The galaxy is subject to, the cluster is subject to the galaxy, and the galaxy is. To simplify the problem even further, this is not how I model it in my code, but just to build more physical intuition, you can simplify the primary and the secondary to be just point masses and put them on circular orbits around one another. And what you do is you can write down the equation for the potential as a centrifugal force and the gravitational forces, and you find where these points balance. And you can write, you call it a constant of motion, which would be the energy of the third body. And you can describe its motion based on its total energy. So if you have really, really low energy, then you either have 2 possibilities. you'll orbit exclusively around your primary or exclusively around your secondary. If you increase your orbital energy, you will open up the first Lagrange point. And this is where, if you're around the secondary, M2, which is the globular clusters, this is where some of the stars escape the cluster. But if you have higher energy, you escape out the back. So this is how the stars escape from the globular clusters, and eventually they create the streams. But this circular, restricted three-body problem gives us the insight and the intuition of the Lagrange points and how stars escape, but it's too simple. The primary and the secondary are not point masses. The secondary can have an inclined and eccentric orbit to the galactic disk. The tertiary can also have an inclined and eccentric orbit, and there are no constants of motion because my Lagrangian depends on time. So you can also build more intuition considering the tidal forces. And to do that, first I also want to break down how you model the Milky Way. Instead of being a point mass, it's a mass distribution. If you had just simple Newtonian gravity, mass times mass divided by the distance squared, but you have to upgrade this because we have a mass distribution. So you go to Poisson's equation, which says that the divergence of the gravitational potential is related to the mass distribution in space. And the important characteristic for me, or in the field, is that this equation is linear. So oftentimes you can decompose your galaxy into different components. I can say that my galaxy, which is shown in this model, is made up of a disk plus a spherical bulge or core in the center, and then also surrounded by a dark matter halo. And I like these two plots because it shows on the top you have the stellar surface density. This is what you would observe. And you can see how it's quite different from the total gravitational field or the depth in the potential well, which shows how important the dark matter halo is to fully quantifying and computing the orbit of bodies in the Milky Way. So I want to show what this looks like visually a bit through an animation. To break it down, here, what I'm going to show is the orbit of a body through the galaxy. And this is the local position vector of the body, its velocity vector, and its orbital plane. And if I put a little sphere around that body, which is representing the globular cluster, I can show how the Milky Way's tidal forces deform this sphere. For those familiar, the tidal force is described by a tensor. So you can diagonalize this and find your eigenvectors and describe it by your principal axes. The blue and the red are axes under which, if you're a star, you're only going to be pushed towards the cluster or pulled farther away. The red and blue are compression, while the green is stretching. So you see that the tidal forces are strongly dependent on your position in the galaxy. And every time you traverse the galactic disk, you'll go through these strong compression episodes where the tidal forces just, if you're along that vertical axis, the galaxy's tidal forces push the stars towards the center of the cluster. And more importantly, though, which is more subtle for the sake of tidal stripping, is how the green axis, which is the stretching axis, increases in magnitude at your pericenter passages, your nearest approach to the galaxy. And this is when you have strong mass loss episodes. And also the green axis aligns with the Lagrange points. And note that it's equal. You push stars out equally in both directions. I would like to briefly discuss my code. I call it T-strippy for tidal stripping Python. I wrote a read the docs page, so it works. It can be used by others. Give a little overview. The computation is done in Fortran. So it uses this compiler called F2Py, Fortran 2 Python. I implemented 2 different integration schemes, and I also profiled my code to know how accurate it is and how computationally expensive it is. I would love to talk about it. But to describe T-stripping in 3 simple steps. Step 1 is that you integrate the globular cluster's center of mass backwards in time. Then you populate that position with a bunch of particles, star particles. And this is a dynamical equilibrium model, Plummer sphere. And then effectively, for each particle, you solve the restricted 3-body problem n times. And you follow the subsequent motion, and by doing this scheme, you ensure that the stream arrives about the original departure position, so where it should be on the sky today. And that's a bit about my method, the physical intuition, and now to start discussing some results. For the first project, a little cute title, A Sky Full of Streams, because we took the globular cluster catalog. Here you have a little sky view of the catalog from Gaia data. And you see that local orbits of the globular clusters are computed, which are the green or the blue lines. And these clusters have uncertainties in their distances to the Earth, their line of sight velocities, and then also these 2 columns over here are the proper motions. So the speed on the celestial sphere in latitude and longitude. And then also we have uncertainties for the mass. We describe this with a 5-dimensional Gaussian distribution, and there is a correlation coefficient between the uncertainties and the proper motion that we take into consideration. And to run this experiment, to consider the uncertainties, we do a Monte Carlo sampling. So I sample this 5-dimensional Gaussian 51 times for each cluster. The 1 time being we take the mean value. And that allows me to explore how the streams, the variance you can get from the uncertainties in the orbits. By the end of this, we get full predictions on the sky for mass loss of the globular cluster distribution. And this is a video made by a colleague, Sergei Kopriskov. I really thank him for making this out of our simulations, where you see a camera panning around the galaxy, just to give you a view of the different streams that you can see. You see that there's a lot of nice, fine, thin ones. We call them canonical stellar streams. But also there's a variety of different types of mass loss, which depend a lot on the orbital characteristics of the progenitor or the host globular cluster. And regarding these simulations, this is for about 155 globular clusters. All of the data is available online. We made our simulations publicly available. And if you were to download them, you would find that a data file contains the velocities for each star particle, the positions for each star particle, and the coordinates in galactocentric, which is Cartesian, X, Y, and Z, centered on the galaxy, galactic, which is another way for the celestial sphere, and the equatorial coordinates, which is also latitude and longitude of the celestial sphere. And in total, we did 51 simulations per globular cluster, 155 globular clusters, and 3 models for the Milky Way's gravitational field, for a total of 23,715 simulations. I want to highlight how the results depend on the different galactic potential model. Here, just to show, it's a composition of a dark matter halo, a thin disk, and a thick disk. It's the composition of this galactic model. And if you were to plot that on the sphere, you could see this density map, where the red dots correspond to the present day positions of the globular clusters. You see many fine stellar streams. And then also as shown in the video, you see a large mess of mixed stars in the center of the galaxy. We have a crude method for estimating the amount of stars lost from all the globular clusters that could be within the galactic field, which is interest for tracing stellar populations in the galaxy. So from this model, we estimate there could be 3 million solar masses worth of stars in the galaxy's field stars that come from the globular clusters. If I go to the next model that we investigated, we added a spherical bulge, not for no reason. There's evidence for this. And you can see that by increasing the mass in the center of the Milky Way, if I blink back and forth, see that there's much higher density in the center. These clusters in the center have faster orbits, shorter orbital periods, they lose mass a lot faster. So with this model, with the stars or with the clusters in the very, very center of the Milky Way, you strip them a lot more and you increase the total mass loss estimate by an order of magnitude. Now there's like 20 million solar masses that could be floating about in the Milky Way. And then we also wanted to investigate at least one model with a time varying component for the gravitational field. We added a stellar bar, and for context, the Milky Way should have a stellar bar, which is a standing wave of stars that just move at a certain angular rotation rate. And with this one, it's a little misleading because here I say it's like an adjustment of the model with the bulge, but it's really more of an adjustment of this model. So that's why the mass loss estimates are more similar, because the mass in the center of the Milky Way is more consistent between model A and model C with the bar. Well, immediately you can see some interesting features that the bar does. If I can bring your attention to this one here at the top, 30 longitude and 60 latitude, you get like a little swirl shape that comes in. If I blink back and forth, it might be a little obvious. Also, this stream is totally inhibited by the presence of a galactic bar. And that's an interesting result, what the bar can do to the stellar streams. And also vice versa, because if you observe some of these characteristics, ideally, we always want to use the stellar streams for an inference problem. What can we learn about the Milky Way given the stellar stream? Moving forward, we can describe the different types of morphologies, because by going into this, we're thinking about stellar streams exclusively, and so we expect to see these long, long, long structures on the sky. However, it depends on the globular cluster. If you have those that are very internal to the center of the galaxy, you have stronger tidal forces, and you end up mixing all of your debris entirely. And so the stars cover all possible orbital positions that the host could have had. And we broke this up into 3 categories. These ones, we called them disk clusters, which are those that live within the galactic disk. And if you look at them on the sky from the position of the sun, you basically see all of the stars just edge on. So you see these flat structures if you could isolate their material from the rest of the galaxy's field stars. We came up with another classification. We called them inner clusters, which is similar, but the globular clusters that orbit outside of the disk. And if you were to isolate them, you would see all of their debris would be restricted here, so a little bit higher vertically. And one other thing that I want to point out, if we take this one here, you can see it quite well, which is that even though all the material is quite mixed, the stars still follow on the orbit of the cluster. So even locally about a given cluster, you may be able to find a stellar stream about it, which here you might be able to see with the density map where you have a higher density about this cluster. This is the case for Omega Centauri. Later. And lastly, if you take our third classification, which would be the outer clusters, so we define this as those that are outside of the solar circle, mostly because if you project it on the celestial sphere, you could expect it to cover the entire celestial sphere. Whereas if you're inside the solar circle, it's only at the center latitudes and longitudes. And once you're farther away, this is when you could start seeing the nice, clean stellar streams that we know. To highlight another result, we also compared this to the observations. And just to show one here, we did this for a couple streams in the paper. The gray density map are our simulations, where the different tracks are from the observations. There's Mathieu, who took a series of different papers and traced the tracks of streams, which is a very nice library to use, very user-friendly. And this allows us to show streams detected from two different works. And you'll notice that these are the streams associated with M68, and this is a new stream that was detected. These are the same. And one thing I would like to highlight is that we have great agreement between the overall distribution we expect from the stream with the observations. So this model, it verifies the modeling approach. And also, you note that our predictions expect that the stream might go to lower latitudes, so within the galactic disk. However, with the stellar crowding, the amount of stars that are there, the gas and the dust, it's difficult to observe in there. And the algorithm wasn't even applied to make this detection within, I don't know if it's 15, plus or minus 15 latitude or 20, but it's not surprising. Perhaps the stream actually is long. Then I would also like to highlight a comparison to this density map in the case of a galactic stellar bar, just to highlight what the galactic bar can do to a stream. In this model, you can tell that the bar model is incorrect because we lose the ability to reproduce an observation. And what you find is all of the debris that we lose is stunted. The growth is stunted. It's located about the cluster. An interesting phenomenon. I don't know if this mechanism is totally understood physically yet, but this is an avenue for future work that I'm quite interested in. But the bar has a very important effect on the morphology and the distribution of stellar streams in the Milky Way. And that is about the first study. The next thing I want to get into is a study in which we, perfect timing, a study in which we try to make the galaxy more realistic by adding more time varying components to it. I would like to give more context and background information. There are these things called dark matter subhalos. The idea is if you start with your cold, dark, your lambda cold, dark matter theory of cosmology, start with the Big Bang theory, the universe was a place of uniform density with only quantum fluctuations of overdensity and underdensity of dark matter. And as you let the universe evolve, these dark matters, halos coalesce and they distribute themselves on filaments, and where the filaments intersect, they're nodes. We call this the cosmic web. And at the nodes, you have these massive, massive, massive halos, which then bring in all of the hydrogen and helium gas to then process it into the stars to create the galaxies that we know. With this cold, dark matter theory of cosmology, the halos are, or dark matter is distributed into spherical halos. And you can have a big halo and subhalos inside of it. This bottom panel is an image taken from the Aquarius simulations. I don't know if this is the first, I think it's the first where they ran this experiment. And just for curiosity, they had halo inception up to the 4th degree. They found a halo within a halo within a halo within a halo. But nonetheless, the important point is that these halos could be orbiting around the Milky Way and they could perturb the stellar streams. And more importantly than that is we could observe these properties in the streams and maybe infer what the distribution is on dark matter on this mass scale. Because the theory says that you should have this distribution function of subhalo masses, which should follow a power law with approximately a slope of -2, and maybe down to indefinitely small scales. It depends on your theory of fundamental physics for what the nature of dark matter is itself. And for now, a lot of the techniques to qualify or characterize dark matter is on mass scales greater than 10 to the 8 solar masses. They use gravitational lensing to map them. So stellar streams offer a way to understand subhalo masses on the order of 10 million solar masses or a million solar masses. However, the problem is complicated because if you want to observe the stellar streams, look at features that could correspond to signs of dark matter passages, you need to assure yourself that it doesn't come from other time-varying components in the Milky Way's gravitational field. So we ran this experiment where we looked at one stellar stream, just polymer 5, and we said, could the other globular clusters in the Milky Way impact polymer 5 streams and create gaps in it, which would be the signs we're looking for passages of objects. This is what it looks like. I have this approximation of a stream moving around, which is just the orbit of the center of mass of the globular cluster, but more or less the stream. And the vectors point towards the net gravitational force of just the other globular clusters. So you can see it's going towards the center of the Milky Way, which is not surprising because the center of mass of the globular clusters is still the center of mass of the Milky Way, except for when you have a closed passage. You'll see that the vectors get deviated and the like. So when you have a closed passage, you may be able to puncture holes in the stellar stream, creating gaps inside of it. And at the end of such a simulation, if you were to look at it, you just might find that a one-dimensional density profile is shown here. Here's the map on the sky. If I project it down into longitude, the black histogram is what we call our full simulations, that in which the stellar stream feels all the globular clusters. And in gray, we have the reference simulations. You can see here we have 2 gaps due to the globular cluster flybys. And that's interesting. We did the same style of experiment where we generated the initial conditions 50 times to get 50 different orbital solutions for each globular cluster in the Milky Way. And then we analyzed the distribution of gaps for each case. We found on average, we get about a bit less than 1 gap per simulation. And since they are my models, I can know exactly what's happening inside of them. If we start with this series of plots over here, it's a 2-dimensional density map of the stream. Just put it in a linear coordinate system. And here there's 3 gaps in it. There's 2 that are prominent, one that's quite subtle. And I have a way to go through and identify exactly which globular cluster caused the gap. And then if I want, I can go through and rerun the experiment with just that globular cluster on to see if I reproduce the gap, and that's exactly what you have here. Then I go through and I tag all of the globular clusters that cause the gaps, and I can create a histogram for when the number of gaps occurred and by which cluster. So I color-coded them, and also a prominent result is that we have 1 gap, which corresponds to the little one over there that happened very recently in the past, and it's because the orbital solutions don't diverge when you go back only a couple 100 million years in the past. This last bottom little histogram is a better way of saying number of gaps per simulation. Instead, you take all the results and you take the number of gaps and you normalize it to per unit length of stream, per unit time. So that way you can compare it to other experiments or studies that would want to do the same thing. It was a study by Kohlberg that first posted this, I think in 2013. I can also show where the gaps happen or where the impacts occur in the Milky Way. The gray density map over here shows the probability of polymer 5 having passed by that point between all of its 50 different orbital solutions that I computed. And the impacts show which perturbers hit the stream and when. So it's not surprising, all the ones coming from the orange dot NGC 2808 all occur at the same time, and it happens in most of the simulations. And then this plot on the left shows the energy, the orbital energy of all of the globular clusters and its angular momentum. And effectively what you learn is that if you're down here, you're really deep into the galaxy's potential well, and you don't enter Polymer 5's orbital space, so you can't impact its stream. Same thing with those that are really far away from the center of the galaxy, which is a rather intuitive result. And then we also asked ourselves, where does gap formation occur preferentially? Towards the interior of the galaxy, where there are more globular clusters, or towards the exterior, when Polymer 5 is farther away from the center? Because there, less globular clusters, but you spend more time there. So maybe you have more time to be impacted. But we did find that it the gaps decrease with distance. You preferentially have impacts closer to the center of the galaxy. Next, the whole goal or ambition is to take the gaps and then infer properties of the perturbator, right? So here I plotted the globular clusters that impact the streams. And we can look at their masses versus their size. So not something too surprising, but it's only the more massive globular clusters, those that are above 100,000 solar masses to 1,000,000 solar masses. But the mass isn't the parameter that's the most important. Instead, you need to consider the amount of momentum that you impart on the stream. So mass is really important. The more massive ones hit harder. There's also the impact parameter. So the closer you are, the more important the impact. And also, you want to go by slower. The slower you go, the longer you apply the gravitational force, and the more prominent your gap will be. And you could take those three quantities and compute the amount of momentum that you give to the stream. And these are all the impacts. And then I also came up with a population of close encounters that did not produce gaps. And you can see that, it's a little tough, but these two histograms overlap. And this means that high momentum impacts are a necessary but insufficient condition to create gaps. And this was something that the reviewer in the paper actually introduced us to do that we investigated much further, which is to consider the conditions in the stream that allow for favorable gap formation. And I think that this is a new result because previously in the literature, I've seen people discuss random motion of the velocities inside the stream that dictate if a gap is going to form or not. This is complicated and busy, so I want to take a moment on this. Starting with the little X and Y panel, this is the orbit of the stellar stream. I'm sorry, in red is the orbit of the stellar stream, and then the black dots are, of course, the star particles. I project all of them onto the orbit, so then I can just create a one-dimensional density map. So this X0 is where the globular cluster Polymer 5 is, and then this is ahead on its orbit, and this is behind, and this is the amount of stars that occupy this position. On the top plot, right, now instead of showing a density distribution, I have a series of just points, where each point represents a star particle, and I color them by when they escape. However, it's not just the escape time, I color them by each pericenter passage, which is when the tidal forces are the strongest, and you have these bursts that come out. You strip a lot of stars at once. And this is a little video, so I'm going to let it play. And what you'll see is that at every pericenter passage, you lose another population that starts going out and moving further away. And then also, in this case, you have an impact that occurred where the stream was only populated by the stars that were stripped at the first Paris-Center passage. So it's a model population of stars. It's one packet, it's one group. And for those familiar with collisionless free streaming, you would know that if you have just one group of runners leaving from the starting line at the same time, they begin to self-segregate. So the faster ones go ahead, while the slower ones go behind. So initially, if everybody leaves with some dispersion of velocity, as you go forward locally, you'll have a smaller velocity dispersion. So in this part of the stream, the velocity dispersion is very, very low. And the criteria that I've seen in the literature is that the velocity dispersion locally, the random motions, needs to be less than the amount of momentum that you impart to the stream. That's the criteria for creating a gap. What we learned by doing this is that if you decompose the stream into different mass loss episodes, and if you impact the stream in a place where it's characterized by overlapping packets, you get this interesting phenomenon, which is over here in case B. The top plot shows the stars that were stripped at the first Paris-Center passage. And you'll note that its gap is at this position. Then, if you look at the stars that come out from the next Paris-Center passage, the gap, which the impact occurred at the same place, right? So here's the first population, the second population, they got hit together. But eventually with time, the gap in the second population goes ahead and they go out of phase with one another. And it's because in the second population, you hit the leading edge when the impact occurred. So locally, you hit the faster stars. And this causes the gap to go out of phase. And then at the end, this bottom panel is a bit busy and messy, but what you see is instead of just a nice gap, you kind of have just a decreasing slope where the gap is shallow and very broad. And this is important. I think this is a new phenomenon that we were able to characterize because what you would want to do is look at a gap and say, oh, if it's really shallow, it was a weak impact. And if it's very broad, it happened a long time ago. But if you don't take into account that the progenitor was on an epicyclic orbit with periodic mass loss, then you'd fail to understand that the broadening of the signal is due to this bursts, these bursts from your Paris-Center passages. Those are my results. I'm just going to wrap up now. So the implications of this new mechanism that we characterized is that there could be more hidden gaps. On an optimistic note, maybe there were more impacts, but they just kind of went out of phase. I don't know how you would do it, but if you had a way to disentangle different populations, maybe you could recover those gaps. But I think more than this, it adds another difficulty to an already degenerate problem of inferring perturber parameters. Then, just to recap, right? So in my first experiment, sky full of streams, we took the globular cluster catalog, thanks to it being characterized with Gaia data and a series of great works from many authors. We were able to predict the first entire mass loss of all the globular clusters in the Milky Way. All of the data is online. It's also already being employed by the community, which is nice. And also, in terms of the second study, we quantified the probability of impact of other globular clusters on the polymer 5 stream. We discovered a new physical mechanism. We characterized it. And at this point, I made my code open source. It's being employed by at least 2 other people. Thank you, Anna. And also Raif, master students, who is helping me find bugs. I appreciate him. And I also think it's appropriate to end on some future prospects, because what's a study if it doesn't lead to anything else? Regarding a sky full of streams, we could think of, What if my models aren't perfect? What if there's some disagreement? I kind of envision it this way in my head. It could either be there's a problem with the observations, meaning that they're incomplete, not that they're wrong. And then you could either have a different physical phenomenon because I'm describing mass loss just from galactic tides. So there's a lot of stuff that's missing from this. That could either come from the internal globular cluster dynamics. There's interesting questions associated there as well. Maybe the globular clusters have their own dark matter subhalo that could be shielding them from the tides, preventing the formation of a stellar stream. Maybe somebody could take my simulations, look at a globular cluster, there's no stream here, what's going on? And then model it in more detail. Then it could be something with the galaxy. Again, the galactic bar, very interesting physical phenomenon, dark matter subhalos, and also mergers, which is two works that I've been able to contribute on a bit. Thank you, Julia. She's in the back. And then there's also another paper from Guillaume in Strasbourg, who just submitted an article as well, talking about stellar streams being sensitive to mergers of dwarf galaxies, which have interesting implications on them. And the other one too, this is a bit more involved. I'll leave this for a question. This is about how I envision recovering dark matter subhalo properties from gaps within stellar streams. So with that, I would just like to take a minute to now in the dark room. It's really dark. I didn't think it was going to get weird. Thank you so much for coming. I have a lot of people who crossed the ocean, and it means the world to me. Thank you, the committee, for coming. Thank you for reading my work. Eugene, I know you've been traveling. Thank you for adding this to your long voyage. Thank you, Paula. I know I pushed your patience. Thank you, Marco. I don't think I push your patience as much, but I really appreciate your time and your availability. I'm sorry if I'm difficult in any way, and thank you to all the girls from Rome who have come. Thank you to everybody from the lab. Thank you to everybody who's listening online. Thank you to the master's program. I've been here for 5 years, and thank you so much. So here's, wait one minute. Thank you for coming.
Thank you very much for this very beautiful presentation.
Thank you, Françoise.
We're going to have some questions now, maybe 5, much more than 5 per person, because we're 8. So George, begin.
Okay, thank you very much.
Yeah.
That was great talk and great work. I really enjoyed reading your presentation.
Thank you, thank you.
So I have a few questions. It's more about, I guess, let me start with technical questions, but I think they are important.
Yeah.
You were showing today that if you have 3 bodies and then you increase the energy of these stars, then you open up more or less a Lagrange point,
Yeah.
and then you have different escapes.
Yeah, yeah.
Now there is in your model you don't include the interactions or stellar collisions with clusters.
Correct.
Which are going to add energy to those particles.
Yeah.
I presume that's going, and because you have probably distribution of those energies.
Yeah.
Some particles are going to get more or less.
Right.
So in terms of escape, I presume that the relaxation of the clusters could give you different stream properties.
Yes.
And from your work showing at the end,
Yes.
we should expect also the gaps to evolve differently if you have
Correct.
relaxation or not.
Yes.
So should we worry about that?
Yes. Yeah, I think so. I think it could be valuable to talk about decomposing the composition of streams in terms of these are populations that were stripped at tidal loss episodes. This is just the leaked outflow, which could be the continuous effect of the tides or just the evaporation process from natural two-body relaxation. And also, there is another study I wanted to highlight, and I have a slide on that somewhere here, which is a paper that did something very similar to what we did, but instead of modeling the tides, they modeled the loss of the globular clusters due to 3-body interactions.
The metaphor for Newton metaphor or not?
The group in Toronto?
Yeah.
Yes, Is the student? I think he's the second author, yes. Yeah, I don't think I'm gonna find out, I don't wanna waste the time either, but effectively you see that it's a much more diffuse envelope. And yeah, the three body interaction, you have the binary that forms, and then the cluster, the star in the center could be ejected with varying velocities, some of them overcoming the escape velocity or not. And so you kind of see, like here I have these nice, thin, smooth streams because the tidal forces just get you over the barrier to come out. But if you have, you know, binary star system, another star colliding with it, you could get flown out. And so you could have different ejection speeds and it makes the stream more diffuse.
So my question, I guess, is should we include that in our?
I think so, because I think, I'm sorry, yeah, I think you can, that population of high escape speeds could begin to fill in the gaps. Yeah, that's what I want to get to.
Okay, so another question that is similarly is difficult as well. So you show very nicely also that we have 120 streams and 160 clusters, but then only 20 have associated.
Right.
So that to me means that a lot of those global clusters were disrupted in the past.
Correct, yeah.
Now, if that's true, you were only using the Harris catalog, which has surviving clusters to inspect the perturbations.
Yes.
How should we model the perturbations from objects that do not exist anymore?
So I did something for you. This is an anticipated question, but it was nice enough to give it to me in advance. So this is what I did. Also, thank you, Gene, for writing a gamma, which is the code I used for getting at this problem. There's different ways you could do it. You could come up with a better way to estimate the amount of globular clusters that could have been dissolved. More of them should be dissolved in the center, less of them should be dissolved in the halo, but I wanted to get a quick result. So what I did is I took the actions for the Harris catalog, okay? And then I did a kernel density estimate, and then I resampled it just to double the population of globular clusters. Then I randomly and uniformly sampled their angles just to offset them. I added mass loss to my code such that, you know, this is an equation I found where they parameterize the mass loss of a globular cluster, taking results from n-body simulations, where you could say it's a function of the current mass, right? So this should be like exponential mass loss, but also a function of the tides, so a function of the orbit. And then, yeah, I added that to my code. I verified that the feature worked. That's as far as I got. I'm sorry. Wow. Okay. But yeah, I think it could be significant.
Okay. So because I cheated, I'm going to ask even a more difficult question.
Yeah.
So there is something that worries me, which is that you know, these clusters are dense objects,
right? And
many of them go to the very inner regions of the Milky Way, a few kiloparsecs from the center. We know that the galactic disk is granular in the center. There are massive GMCs with masses 10 to the 6, 10 to the 7 solar masses. Yes. Nowadays, including GMCs, as far as I can tell, or very few people, as far as I can tell.
Right.
Now, another problem with GMCs, they only survive for a few 100 million years, not even one orbital period around the Milky Way. Yes. How should we model those?
Okay, great. There's another paper that did this. So I'm taking from this. I'm convinced by their methods. So we also wanted to investigate this, and I think we want to do this further because the other study wasn't looking at stellar streams in the Milky Way context, just stellar streams in general. What can molecular clouds do? So the first thing I checked is that the lifetime of the molecular cloud is larger than the interaction of an impact. To do my due diligence, I thought so. An impact has a duration of about 105 million years, so not too long, which is much shorter than the lifetime, so that's great. And then what this paper did, and I think it's okay, is that you do a Monte Carlo simulation of specific streams, and then every time you do one simulation, you generate a different distribution of molecular clouds. I don't know if they used an empirical law. I don't know if there's a theoretical law saying you should have this many clouds here, and this is how massive they should be, but something of the sort. And they didn't include dissolution or not, but if you just assume that every interaction is totally stochastic, you should be okay. Because the only problem by not including the dissolution is that this specific orbit of a molecular cloud will come and hit the stream twice.
That's right.
So, but if you do high enough sampling, you should be okay for that.
Okay, and my last question, very brief, I had to ask this one.
Yeah.
You assumed that the Milky Way is static
I did.
for the last 5 years.
Yeah.
How much freedom do we have to relax that assumption?
There is a paper, I forgot her name, I think it's a group, Sergey sent me the papers, but they did merger history analyses of the Milky Way, and they posit that the last major merger that significantly increased the mass happened 8 billion years ago. I could even find the paper later if we want to do this, but also it shows that the mass increase since then does not significantly change stream properties. It might deviate the orbit a bit more in the past.
Yeah,
but
in the Milky Way, we know that's not true, right? Because we do have the LMC coming in now. So
yeah,
those statistics are not relevant, perhaps, for our galaxy.
Okay, great question. I also prepared for the LMC.
That's my last question.
That
was successful.
Yeah.
Glad you brought this because I basically looked at the paper from Belukurov, 2023. Which is really nice. I learned a lot reading this paper. Here we go. Okay. So there's one stream in particular. This is one of those, I don't know, Paula and I were speaking about how sometimes the names in astronomy are funny. This is a stream without a cluster. They call it orphan. If you look, this is the stream track. And you know, the idea with the streams is that they're co-moving, so they should be moving along the same line. But the presence of the LMC is deviating part of the stream over here. And two things. How important is the LMC for understanding the Milky Way's gravitational field today? And is it important for every stream? I think it's important for some streams, not every stream. There's Rodrigo's paper, 2024, where that wasn't included, and then you're able to find a great model for the Milky Way's potential by just using the streams and axisymmetric Milky Way without time-varying components. If you want to get more specific, you can look at this stream, Orphan, and they did this MCMC analysis where you could come up with a model for the orbit of the LMC, the mass of the LMC, the size of the LMC, all the Milky Way parameters, and then you can even use the stream to recover the mass of the LMC and its profile, and when its last infall occurred. And yeah, they had this stuff here, which is like fine-tuning the properties of the LMC. So I think it depends on the stream. Yeah. Thank you.
Thank you very much. So, Annalisa, the second record.
Thank you very much. I really commend you on two things. I think the originality of the decoherence mechanism that you identified and brought to light, because it's a very crowded field of research, as you realize.
Yeah.
And these are crowded objects by themselves. And since to come up with an original idea, especially nowadays, is difficult.
Thank you. Yeah, it was hard.
but you kind of naturally, I think, reached this realization over a period of time. And I think it was very, very beautiful the way it came about. And the other thing, you're a wonderful presenter and a very effective one. So this.
Thank you. A lot of practice and people to listen to me.
So you think you know that I like Gobler cluster by themselves, together with everything that they do for the galaxy. So now my question will be more related to the progenitor themselves. So I'm pleased that you have in the second half of your final slides a lot to do with this and the internal dynamics of Gobblers in particular.
Right.
So a practical question first, can you tell us how you actually design your escape criterion? I know that you run this through at the beginning of your presentation, but you can kind of repeat. Exactly, once you're putting your progenitor star cluster close to the location which you start losing stars, you're having a star that is being launched by the Lagrangian point.
Yes.
How you decide for that star to be actually launched?
Yes. Perfect. Okay, so this is perfect. I don't need to do anything here. For restricted three-body problem,
Yes.
you could say centrifugal potential, and then the primary and the secondary to find good approximations to the Lagrange point, and then maybe use like a radial distance criteria for when you're beyond it to say this is when we're outside. That's not what we do.
Good.
Great, okay, good, perfect. We just use the two-body energy criteria, which is not perfect, but generally it works. And you can see the imperfections on this plot, because you might have some that leave and then still actually come back in.
Very good.
Yeah, and that's exactly, do you see these points here?
Yes,
So they got flagged as being escaped,
yes,
and then they actually never left. Yeah,
very good.
Okay.
This is excellent because this is also consistent with what we learned from collisional evolution. So we call them occasionally potential escapers.
Okay.
So they are almost there, but not quite.
right,
And they can be long-lived within the context of the potential of the secondary. Yes.
yeah,
And so these do come along also with collisional implications. So
Yeah.
this is something beyond what we can explore, but it's good that you have the skeleton of these orbits,
Yeah.
even from the collisional perspective.
right.
So related to this point, have you, maybe you didn't, but feel
Yeah.
free to reply honestly. Any asymmetry between prograde and retrograde orbits within the progenitor itself, in the sense of, are you preferentially launching off in the streams, stars that are prograde or retrograde?
I have to tell you, I've never looked at an orbit inside of the cluster.
There's a whole new world in there.
I know.
But this is where I think I would suggest another, this is well established in our side of the story. let's
Yeah,
say,
yeah, of course,
so
of
that
course.
We know that there is a preference for one direction versus the other one, and it's very much linked to just the basic nature of the three-body property itself.
Yeah,
So this is something that I think can have ramification onto the decoherence mechanism too, because you might identify, I really like your analogy for the runner mechanism.
yeah,
And some of those runners, the one speedy one
Yeah.
in front of it, might come with an origin that can be prograde or retrograde preferential.
okay,
So we can discuss this separately.
okay, yeah, I would like that. Okay, great,
And then my final point for this, still related to the thermodynamics, if you don't mind.
right,
There is a whole richness associated with the progenitor itself.
Yes.
And the dynamics.
Yes.
And you mentioned some elements. What would you say to me if I were to encourage you to consider a progenitor cluster that is actually rotating?
Yeah, what would I say?
Mhm.
I'm curious about that. I was reading about how there is evidence for counter rotation inside of Omega Centauri.
Yes,
And I'm still curious of that because for me, rotation means flattening and creating a disk.
very good.
So I feel as though once you break the spherical symmetry,
Yes.
you would break that immediately. And then also I'd be curious in terms of how that does change the mass loss evolution and also how that changes the configuration of stars within the stream. Particularly, I'm just
Yep.
speaking, okay. There is, I don't know if I'll be able to find a plot. Yeah, there's one thing that I have a problem with all the time when I see simulations like mine with this approach of simplifying the streams and only focusing on the tidal component, which is if you look, it's really subtle, but you might see that there's these overdense streaks.
Yes,
So I think that these are epicyclic overdensities.
Yes.
That does come from when you have your pericenter passages. And I just don't think it's going to be that neat and organized. And I think this escape from evaporation processes
yes,
would absolutely make that a bit more noisy and decoherent.
Yep.
So that's my expectation. And then also in terms of, do I expect rotation to stunt mass loss or increase mass loss? I'd only be guessing. I'd imagine it depends if you're spin aligned or
yeah,
Or
so
finalize.
all your intuition on the spot is correct. In the
Okay.
sense that all these things do matter, and
Yeah.
we do have some established knowledge about this within the context of collisional simulation. But also another very basic element that I think goes well with the context and your way of operating in this problem, which is just the effect of angular momentum for a single star onto the Lagrangian point. So
Yeah.
you're positioning your particle onto the Lagrangian point.
yeah,
And this particle, which is kind of having some degree of angular momentum by itself, by the way in which it's contributing to the global angular momentum of the
Right.
projector, will know left and right probably better than you. This is what you were saying left and right on your screen. So they will in fact know about this, and they might also have implication on the way in which the gaps are generated in sort of a generalized epicycle theory that one can come up.
Right.
So all these things do matter, and I think it's another area of slightly room for discovery in the context of.
Could I ask a question?
I don't know.
This is the counterattack I was talking about. Because streams are supposed to be the inferential tool, and there's also the question of multiple populations in stellar streams, and there's also the question of different formation mechanisms. Oftentimes, it's understood as different generations of stars, and so second generation stars born in the center in a disk that would have a angular momentum parameter, and so that could absolutely be mirrored inside of the streams.
Yes.
So I was thinking about ways of, if you were really able to flag which one's second generation or second generation, how could you use that to reverse the mass loss history and the internal dynamics? I was thinking about that, and now I feel like this is one way to do it, is to know evolution and angular momentum internally.
Yes, certainly, and I think thanks for the question.
I don't know if you've thought about this or
but it's certainly relevant. I think you're at the stage, particularly because what you need as a zero-order piece of information is the chemical tagging for the stars within the tails, and we're getting there. And it's expensive and difficult to do. But all this inference, of course, is also a very degenerate problem. As I also
super degenerate.
So we need to be clever.
Yes, indeed.
Thank you very much.
Thank you so much.
Okay, thank you. So I will follow the order. Christian.
Thank you. I'm a bit caught by surprise because I don't know whether I have any intelligent questions to put now after all this, the great questions that were put to you by Annalisa and Jorge. But I do have some questions. I think I'm going to focus on what was being said about the setting, the way that you set up your Milky Way system. So you saw that the bar, for example. I wonder if we could have a little bit more information about how you set up your bar system. Or these calculations, because you did see some significant sensitivity to.
Oh, absolutely. Absolutely.
Would like you to comment a bit more about, say, what was the pattern speed?
For sure. I have
Was it a steady state bar?
Yes, as in terms of
Constant.
Yes, we only ran simulations with constant bar pattern speeds. Can I show you some plots?
It's I didn't write the slide number, I'm afraid, but 33 or something. Oh yeah, okay, 100.
I know. I'm sorry. I was throwing them in here like.
Let me put the question to you. It's a simple question.
Sure.
We saw that some of the clusters that you were dissolving more efficiently.
Right.
Would some of them be actually caught by the bar?
Oh yeah, in terms of.
Did you see that in your integration?
I think I could. I haven't investigated the bar effect on because when I read about the bar, I'm only really familiar with the Lindblad resonances and talking about the bar's effect on disk orbits. But it has a really strong effect on these halo orbits as well. And I have this. May I show? Okay, cool.
You're the boss.
Where effectively these are a series of different simulations, and each of them have a different bar pattern speed. I don't quite understand how this mechanism works entirely, but if you get to some pattern speeds, all of the material is completely blocked around the cluster. Maybe you've got some type of moving potential that you're locally in a minimum of and you don't escape. But there's quite a number of streams that are sensitive to this.
These inner cluster are more or less isotropically distributed on the center. Or did you actually say, I have a bar now, therefore I will not sample the orbits the same way?
I'd still sample them in exactly the same way, just see what happens.
So the answer to that question actually is in your data cube somehow.
It is, yes.
Right. So, oh gosh. I mean, I have many questions, but I don't know which order to put them to you. Maybe the last one, because it struck me that basically you said you were modeling globular clusters, but effectively we could be applying this to dark matter clumps. dark matter itself.
Yeah.
It should also be dissolving in the same way.
Tidal stripping, yeah.
Because there's no collision.
Right.
How about that?
How about that? How would I?
You think micro lensing, for example, might be able to, because these would be streams that are invisible.
Yeah.
So
what's my take?
Yeah.
I gave a talk last year.
No, talking about what you're saying now.
Right.
Last year, now.
No. Okay, so right now, there's a paper I know that talked about microlensing for dark matter subhalos. And so extragalactic, right, outside the stellar stream context. And I don't know, maybe the host of the galaxy was 10 to the 11 solar masses. And then they said, maybe by deconstructing the lens, we see that there's a clump and an overdensity. This could be a dark matter subhalo on the scale of 10 to the 7 solar masses or 10 to the 6. But they preface this is just a 1 sigma result, we're not too sure. So in terms of the lensing, I think that
So the convolution is difficult.
the convolution is difficult in terms of lensing. In terms of gravitational lensing of small dark matter clumps in the Milky Way, that could be in the order of 10 to the 5 solar masses. I don't know. Probably not anytime soon.
Could we look at the Palomar modeling that you're doing?
Yeah.
Because at some point, I think it's a half kilometer per second. I think that the velocity dispersion in the tail there. But it's on the scale of a few, or maybe 1 kiloparsec.
Yeah.
Whereas when you look at see your gaps there, it's several kiloparsecs.
Yeah.
So do you actually, with your modeling, when you look at the smaller, closer to the cluster, do you actually see these epicyclic things and like the linear analysis basically? You actually recover the structure that we see on a smaller scale, closer to the...
Yes, absolutely.
Do you have an example of that?
Yeah, for sure. I have let's see. I think it's visible in, or best visible. Well, actually, yeah, you can even see it here, right? Because when I let this go, I color code each individual packet, and this is when you escape at Paris-Center passages. So these are the epicyclic overdensities. And you do see it in the general stream morphology in our simulations, for sure.
Well, my own feeling about these things is that because I misunderstood how you were modeling your clusters using a core. And basically, when you talk about quantum modeling, you mean the core, the inner half mass, say,
Would I? Okay, yes.
And then you have your halo stars. That's the ones that are interesting to produce.
Yes, what I do is I say the globular cluster is a Plummer sphere. So I have one mass parameter and one characteristic radius. And then I say that I use the dynamical equilibrium model, so the velocities are distributed isotropically, so equally random in all directions. And I sample it appropriately, so I don't like cut out the low energy stars inside that should be more collisional, they're still included in the model. It's not just the outer stars, the globular clusters.
Right.
Yeah.
Okay, so the Plummer thing actually covers the whole cluster. Okay.
Yes, yeah.
Because when you go through this first passage, because my understanding was that basically you have to reset your cluster because you may lose from the sides and mass at the first shocking, disk shocking, for example.
Yeah, for sure.
And so it knows. So basically, the first orbit is important because it doesn't know the shock that's coming to hit it.
Correct.
But the second time around, it does.
Second time it does. In terms of, are there imprints
the tidal field, so the Roche lobe.
Yeah.
The Roche lobe has been filled,
right?
But it's fixed from the first Paris-Center.
Oh, I see. You're just talking about the distribution of orbits inside the cluster and how those change with each Paris-Center passage. Oh, yeah, exactly. So here you can see with this model, it's absolutely the flaw. And if I were to start over, I would do something more clever or different. But you see, because we took the catalog and we just say, let's run it as it is and see what happens. So you see that when I populate the globular cluster with stars, many of them are outside of the Roche lobe. So you lose a lot at the first Paris-Center passage. And then afterwards, you would approach a more steady state where the loss of stars is just
Can I ask one more?
Well, just one, yeah.
Just one, huh? I'm on the leash now. But that's fine. I should not, because if we could talk about this for a long time. It's about the five PPE thing. The 5 PPE thing.
Yeah.
When you realize that if I were to overflow my Roche and I go back in time, actually I will generate these streams, and I have enough time to catch up with the old stars. Escape from the ones that are leading.
Yes.
I will catch up because I'm going the opposite direction. So that's really I can catch up with them.
You're talking stars still orbiting the globular cluster?
Because the correlation is phase-based.
Yeah.
You stay close, very close to the original orbit.
Yeah, absolutely.
So you not see that sometimes you actually catch up with those stars that were ejected. So in your integration, you actually remove this, you don't remove the stars that were feed them to the stream, right? So do you see them actually being reintegrated in cluster?
Oh yeah. A little bit. It's shown actually here. This is also about like the escape criteria that I used, where here we just use the two-body escape criteria. So if your kinetic energy overcomes the gravitational potential, I flag it as being lost. That means you have a very outer orbit. But then, this graph, this is the escape time. So I flagged it as escaping there, but it actually stays in the cluster and begins reorbiting around it. And then eventually, it leaks out again, and then it starts integrating within the stream. Yeah.
So it's not like you flag it and you take it out.
Oh no, yes, I'm sorry, because there are methods that do differently. They say flag it when all the stars escape and then integrate forward. I don't do that. The integration is consistent or continuous between internal and external.
I would have liked to ask about the methodology, the numerical integrators, but I think maybe Eugene will do that. But there will be more. I would love to have some more discussions.
Yeah, for sure. I put a lot of time into it. I'd love to talk about it.
Good stuff. Thank you very much.
Thank you for your questions.
Nice presentation.
So now, Eugene.
Okay, well, prompted by Christian, I have to how would you compare your methodology with the other generation methods, like Lagrange cloud stripping, particle spray?
I was looking into this quite a bit. How would I compare? So I would say mine is just the tides, right? So we lose information on the internal dynamics. However, are you familiar with the Fardel model?
Yeah, I think it's the particle spray.
Trade. Right. So this one I think is the one I've seen most employed in the literature, and the way they did it, because the earlier methods was just, I'll generate particles at the Lagrange points, and the Lagrange points aren't necessarily static, they might change based on the orbit, and then maybe at every Paris-Center, like at a fixed time step, I'll just generate a particle and shoot it. So that traces the track of the stream quite well. But then you would lose any internal structure that would be caused by the galactic gravitational field, besides the fact that your orbit's slowing down and speeding up as you go from Apple-Center to Paris-Center. And then I know with the Fardel models that they did a parameterization of n-body simulations to construct their mass loss rate. So that is pretty much what it is. I think if you're inside of the grid of n-body simulations, you're good. But once you go outside, you extrapolate. And it's a different modeling approach. I wanted to look into this more. I tried using Galpai's method for it, but then I got caught in that classic trap of, I can't figure it out. Is it going to work the way I want it to work? Am I going to have to mess with the code? And so then I just pursued writing the code myself. But I'm interested in investigating more particle spray methods because really by increasing the computational time, you could run the simulations in the dynamical time of the orbit of the globular cluster in the galaxy, and that would save a lot, especially if I want to really increase the parameter space. So I think this method, as long as you know it's just restricted to tidal stripping, you're never really extrapolating if you know how to interpret the results correctly. So you don't need to depend on previously processed n-body simulations. But I don't want to rule out particle investigation, particle spray for my own future work at all. Yeah,
I would agree that in principle, as you said there, and they are calibrated against the body streams, but in most cases, the particle loss is actually constant in time, whereas in your case, you probably lose more particles at the horizontal passage because the tidal field is stronger.
Right.
So at least in terms of the stream structure, it should be somewhat more realistic.
Right.
Yeah. At the expense of more computation, because we can configure all, it's not just the particles lost from the stream, but
Also those on the
also the
inside.
ones that are in.
Right. Yeah.
Okay, so the next question is on the first of the two papers that you're describing in detail.
Yeah.
When we see this sky full of streams,
Yeah.
basically it feels like every global cluster has to produce a stream.
Correct. Yeah.
Whereas in reality, we observe them, as we say, in a far smaller number of cases.
Yeah.
So what do you think is the main reason for the discrepancy?
A couple things. Yeah, I think it's the different physical mechanisms at play and also the observations. There was a paper just published by, let's see if I can get to it quickly. Here. This is by Pete Kozma. And I almost got the impression looking at it where it's like, why aren't the observations consistent with the simulations? And then by reading, I'm like, why are the simulations consistent with the observations? So here, you're familiar with the precedent survey? I think I understand the methodology quite well. It's almost analogous to the distance ladder type computation where you can, you're able to build the associations between the stars within the field to those within the cluster. And then, yeah, you kind of just see like sparse debris here and there. In this paper, they said that, we could have a bias where we're just observing giants. So maybe the sampling is much more stochastic, and that's why we're not getting any structure that emerged yet. So at that point, you can say, in the future, there will be better observations and maybe coherent structure will observe. And then also in my simulation, it's clean tidal loss. So there is here's the slide I wanted. This is the experiment by the group in Toronto, where they called it core spray, 3 body interactions in a core. Yes, yep. And this is a comparison of the polymer 13 stream from our simulations in yellow, and then their simulations in blue. So when you have different mechanisms, that completely changes the morphology of the stream, and you also get much more diffuse structure. So that could be explaining, for instance, that which you see here. Because here you're seeing stars that are completely not just perpendicular to the orbit, but rather diffuse along it. So they may have escaped from 3 body interactions instead of just leaking out the Lagrange points from tidal forces. And then there's also everything that's happening in the Milky Way that could wipe streams away, disassociate them with the current clusters. And so, yeah, there's the Omega Centauri, which has the 2 streams associated with it, with one that's like quite removed and further away, and instead of being nice and continuous and attached to the body. And so that could absolutely be in play for a lot of cases here.
Yeah, maybe another thing that I could relate to that is that Christian already mentioned that, or is the discussion with Christian, that when you're sampling the initial conditions of the plumber sphere, there are a lot of particles, but some particles outside the initial tidal radius, which will be immediately lost, form a stream. In reality, probably that's not what's happening. The cluster would be truncated at the tidal radius from the beginning, so you would not produce the streams from the clusters that are on the wide orbits, because I noticed that apart from a couple of clusters in like at 100 kiloparsec, all other clusters in your streams produce some sort of streams, which probably is not very realistic.
For sure.
The tidally limited and the underfeeding.
Absolutely.
So maybe these the initial conditions could be sampled in a slightly more sophisticated way.
I also think too it's from using a plumber, because if you upgrade to a king, then you could have the concentration parameter, and then that could also protect you a lot more from the tidal truncation. I implemented that in my code a couple months ago. It was slow. I need to implement it better. But yeah, no, absolutely. So for instance, there's some of these outer halo streams, and even too, I think this is an absolute artifact of the methodology. You'll see these diffuse clouds like this here. I think is quite due to the. Oh, I'm sorry. Like you see this one at the top right. I think that diffusion absolutely comes from at the initial beginning of the simulation by using the same half mass radius of the plumber sphere. You have a lot that are beyond the truncation limit.
Yeah, okay, so then coming to the simulations of Pal-5.
Yeah.
As you probably know, the cluster is believed to experience a lot of mass loss in the past, whereas in your sims, it's assumed to be the same mass at the beginning as it is right now.
Yeah.
So which is a simplification that could be justified somehow, right?
Yeah. I think it's a strong simplification. I
It's a
do
strong
think it limits the
simplification.
results.
There are reasons for doing it this way, but of course, in reality, it's not.
No, for sure.
So what do you think would have changed if you were to evolve the cluster with a larger initial mass? And how would the property of the stream change?
Yeah, I think regarding the, right here, you see it's like bimodal, like there's unimodal depending on what side of the stream you have. This large peak, I think, is the mean drift rate from how far all the particles were lost at the beginning of the simulation, and you just let them drift freely.
Mm-hmm.
So that structure would change entirely.
Mm-hmm.
I think you would have something that's a bit more flat. And also the fact that, what do you call these things? The exponentials, the mass, the rate at which you lose mass is proportional to the mass itself, and also the strength of the tidal field. That's absolutely going to change the density profile and also the composition within the stream itself.
Mm-hmm.
In a way where we have this result, which is not new. I've noticed it in some of the papers by Bovey, Sanders, and Urkel, where they know too that preferentially you'll have gaps at the farther edges of the stream because this is where the velocities are more self-segregated and ordered and therefore colder. Yeah, here since we have strong mass loss at the end of our simulations, I think it makes the region around the globular cluster really just dominated by epicyclic mass loss, and makes it even less favorable to gap formation. So I'm wondering if the gaps would occur more because you would have more space in which they could occur. That's one thing that I've thought about. And yeah, the density profile would be totally changed. If I could do it again and republish the paper, I would absolutely include a stronger initial mass and then have a mass loss of the cluster. But yeah, we started with take the catalog as it is, and we kept going.
Mm-hmm. And maybe a last question generalizing these things is, we have made a number of approximations in this work.
Yeah.
What do you think is the most serious approximation, or kind of least realistic one? And secondly, which might not be the same thing, which one you would like to lift first?
Which one I'd like to lift first? Well, actually, on this topic, because the second paper is just about polymer 5. So I would have liked to gotten polymer 5 more right, a more realistic model for it. I do think what's great about the work is that this mechanism is going to be independent of the internal characteristics because it's the mechanism of gap decoherence, which I think is a valid and new exciting result.
Mm-hmm.
I do think that the gap statistics are, well, we talked about this. I think in the case of polymer 5, it's an overestimate. However, a lot of these streams that are unassociated with globular clusters, they could have been evolving continuously without being repopulated and refilled. So they could be getting colder and colder and colder and colder. So with some of them, they could be at this temperature to be able to receive gaps like polymer 5 does from other globular clusters. But I think that that modeling limitation does take away from the generalizability of the statistics of the gaps on polymer 5 for globular clusters. And that would be the thing I would want to get more right. And then, yeah, the other categorization of stuff in terms of the Milky Way, yeah, they're limiting assumptions, but I also see them more as future avenues of investigation. So how, like the Milky Way has a bar, right? How does the bar impact the streams? And more of a future work than like limiting what we've done before, I would say.
Thank you.
Yeah, thank you for the questions.
Yes, I'll try to be quick then. So I'm probably the only non-expert in dynamics here. And so I would like to ask you, so first of all, I really enjoyed reading your thesis and I really enjoyed your presentation. So very, very happy to participate in this committee.
Thank you.
And so my question is more on the global picture, right? So in terms of evolving gravitational potential of the Milky Way, we know that having a fixed gravitational potential is quite a strong simplification,
Yeah.
especially if you consider that globular clusters are likely to form over 12 gigayears, if not more.
Right.
And so you mentioned in your thesis some work that has been done assuming and using cosmological simulations like the Lassus DNG. So my question for you is, how do you think this would affect your results, evolving your globular clusters over a much longer time scales and in a time-varying gravitational potential?
So there was the work by, I might have the wrong last name, I think it's Yushenko. They were the ones who were investigating the merger history of the Milky Way and how much it would have an influence on the stellar streams. And they did posit that it's likely that there wasn't a big mass increase episode. Our last one was like 8 billion years ago. So by picking 5 billion years, the Milky Way should be axisymmetric and static enough where maybe the constants of motions are preserved well enough where we absolutely do not have the correct orbital trajectories, but in terms of it occupying this orbital space might be appropriate enough.
Yeah, but my question is, what about the previous 7 years? I mean, this globular cluster may have formed much earlier than the last 5 gigayears. So I agree with you that, assuming a static potential in the past 5 years, it's a good approximation.
Right.
But in terms of the effects that the previous evolution would have on the globular cluster.
Okay, I got you. Okay.
So
so there's are you familiar with the in situ population and the ex situ? Those form. Okay. So the ones that were imported from dwarf galaxy mergers, I think they had streams before. These are the simulations that Julia did that you really do not preserve the constants of motion. The angular momentum's gone, energy's gone, and then it arrives at a point and then it kind of stays there. So I think that means that if you strip material previous to entering or while you're entering, you wouldn't be able to associate it with the cluster dynamically, just chemically. Then there's the thing that I wonder about is, could some of these streams stay coherent as they enter and just be detached from the cluster? Maybe less convinced on that. I think you would probably lose coherence, but maybe not too much, and that could explain some of the streams that we see today. Does that answer your question?
Yeah, I mean, from a numerical point of view, do you think it would be realistic to implement your approach in a full cosmological context, or it would be, from a numerical point of view, prohibitively?
I think you could parameterize the parameters of the potential model as a function of time. So if I wanted to do something simpler, maybe I could use a basis function approach for the halo with the spherical harmonics. And then I could say, based on the cosmological simulations, these are how the halo parameters change as a function of time, which should be realistic enough, and how do the streams respond appropriately. Yeah, that could be done. This is a similar work to what the paper that we're collaborating on and Klensburg is publishing, is how do the streams change in the context of mergers. And
because this has major effect also on globular cluster survival itself.
Yeah, absolutely. There's also the work by Sarah Pearson that I referenced in this, where they talked about the amount of streams and globular clusters that we should have in the cosmological context. And yeah, they were able to use that to estimate the total number of streams that we could possibly observe. And they put that number at about 1,000 streams. So we should see more.
So my last question is, you have all this data, amazing simulation data. Do you think it would be realistic, since in the end what you want to do is an inference problem? You want to learn something about the Milky Way from the simulated stream.
Right.
So do you think it would be realistic to do a global fit instead of trying to fit the observations and streams one at a time?
Yeah, there was the paper by Rodrigo Ibarra, published last year that we collaborated on. What was done was fitting a subset of streams. So a subset, I think it was 20 streams, which are the longest, which then sample a wide range of radii and elevations above the galactic disk. And with that, you're able to constrain a large part of the potential. However, they purposely avoided the streams that were on the interior of the galaxy, as you would expect the bar to be quite perturbing and outside of the scope of the work at the time, but absolutely could be used in the future to constrain bar parameters. And then also too, there was this orphan stream that was explicitly omitted from the analysis because it is strongly perturbed by the LMC. So yeah, in that case, it was 20 streams were used to global fit the parameters describing the Milky Way, where you have a couple like disks, a halo, and figure out their characteristic masses, characteristic radii, and the fits are quite good. Yeah.
So it is doable.
It is doable, yes.
So the very final one. So in terms of gaps.
Yeah.
I mean, from a simulation point of view, if you simulate the Milky Way and
Yeah.
simulate, the warps entering the Milky Way and coherently with their stellar population and black hole population, you would expect from most of the simulations a large population of wandering
Black holes.
mass black holes.
Yeah.
So would this affect somehow the streams? I mean, I know that this is not something that you have worked on, but you may have gained some intuition in that.
Yeah. I have done some literature review on the intermediate mass black holes. I know people are curious about the globular clusters, could be their origin. Or there could be the remnant of a globular cluster that's just a little cluster of black holes flying around that could be more than just one black hole, therefore more massive, and then also perturb a stream. It does look like that in terms of causing a perturbation on the stream, you need at least 10 to the 5 solar masses. Honestly, it could be 6, 10 to the 6, because we're looking at a case where the stream was particularly cold, really clean just from tidal forces. The moment you complexify the gravitational field more, you'll have more of a dispersed structure.
Very, very simple. So if you have, traced the flybys with globular clusters and the effect that globular cluster have on the stream. Suppose that, for each of these, instead of having a globular cluster, you put the same mass into a black hole. What would be the effect?
What would be the effect? So it would absolutely still have a collision. And yeah, if by parity of mass, you would absolutely form a gap. I have this plot. I wonder if it would be easier for me to draw it. Ma'am?
Yes.
Okay, thank you. This isn't gonna work. All right. Imagine an x-axis. This is the, this is the stream, okay? The impact occurs here. I'm the impactor and I'm flying by perpendicular to the stream. I'm gravitationally attractive, so I pull everything on the right to the left, and I pull everything on the left to the right. So then what happens is the particles overtake one another. Once that passage happens, that forms a gap. There was a work by Urkel who first proposed this theory and looked into it. And I think later Sanders, Bovee, Vasiliev looked into extending this more from just a point mass or from just a plumber sphere, even considering like, what if you have an extended NFW halo dark matter? And effectively, what matters for the magnitude of the strength of the kick is mostly just the mass. And then if you're more extended, maybe the strength will be a little bit weaker, but you also pull a little more particles on the side. So by parity of mass, you'll absolutely still form a gap and kick it. It's just the flavor of the kick is a little bit different. Yeah.
Thank you. So maybe I will take 2 minutes to pose a few questions.
Sure,
Well, first I congratulate you because it was a very hard work and very beautiful presentation. Well, in fact, the use of these streams at the beginning was to know the flattening of the halo. And I noticed that in your 3 models of the galaxy, it was only spherical.
Correct. Yeah, correct.
Do you think that there are still some things to use about, because in the literature there was debatable things, some found that it was spherical, someone flattened or even polar, I don't know.
Yeah.
So do you think there's something to gain on this?
Yeah, in the Abata paper, yes, there's 2 things that I can cite about the flattening of the dark matter halo. One particular is actually the Belukhanov paper for investigating the LMC. And they said, what if I have a prolate halo? What if I have an oblate halo? And what if I just have a spherical halo? And interestingly, to my surprise, the spherical one was the worst. I would have expected prolate to be the worst. I don't know why, but both of those were better for their MCMC fits for the gravitational potential of the Milky Way, for creating the orphan stream, and for fitting the LMC orbit. And I know in the Iwata paper, with using all the stellar streams to characterize the Milky Way's halo, it is a flattened halo model. And yeah, he recovers the flattening. It's also consistent with the result from Belukadov from just using the orphan stream. What is this number? I don't remember. Is it like 0.8 flattening coefficient or something of the sort? But yes.
So it's still possible from the streams.
Is this possible the streams to recover the flattening of the Milky Way halo? Absolutely.
So
Yeah.
about the gaps, you said that maybe globular cluster can do this and not the dark matter halos. But the GMCs that to follow George maybe more likely because in fact they are in 2D.
Yeah.
And all the globular cluster pass through the galaxy.
Yeah.
So they always find a GMC. While in 3D it's more rare to find another GMC to find. So don't you think this is the main factor to have gaps and you have to simulate that also?
Yeah, that's a great point. Yeah, actually, I have the selected result from the Amorisco paper, where it does show that I'm actually wrong. Earlier I said they just created a fake stream. It was actually the polymer 5 stream and the GD1 stream. And that acts as symmetric Milky Way with a giant molecular cloud population. And the streams get cut up. They absolutely get cut up by the, I gotta find it. I thought this would be easier when I threw 100 slides in. God. Not gonna be easier. Anyway, I'll just throw up a random slide. Yeah, they do make up this has nothing to do with what I'm talking about. Yeah, just too dark, I'm sorry. Yeah, they absolutely do. Like, there's a lot of gaps inside of it. And to be honest, this experiment, to give the backstory, originally we wanted to go right for the dark matter subhalo population. We were like, okay, we'll have to do something clever to sample that. So why don't we just start with the globular cluster catalog to verify that the code works? And then we saw gaps and we were like, okay, I guess we're doing this now. But yeah, the giant molecular cloud population could be more significant than the globular clusters. I have the intuition inclination to think that it would be.
Because you have 160 globular clusters and like thousands of GMCs.
Yeah.
Well, and also the last one is I found very interesting that you find some shells.
Oh yeah. Yeah.
So do you think that these GC making shells are completely destroyed and make some radial orbits, or can you find what kind of orbits are these who make shells?
Yes. How does the shell works? Regarding the phase mixing, right? You have all the different possible position configurations available to your globular cluster based on its constants of motion. When you begin to populate that enough, you can see that you could have stars occupying every single position available to the cluster based on its orbit. And if you look at that on projection, you see the shell. So I think it's a natural consequence of the material being phase mixed enough and then looking at it in projection. In terms of which ones, yeah, those that are phase mixed enough, like the ones that explicitly you mean in the inner regions of the galaxy, like.
So it gives you some information on the bulge, on the concentration of the bulge?
Does it give you specific information on the bulge? Can we look at this again to make sure we're talking about the same thing? So by here, like sometimes I kind of see like these shells like this, right? Yeah. Yeah, that comes from, like if you have your orbit of a cluster, you'll have your maximum radial extent, you also have your maximum Z extent. And so that just kind of processes around the pole. And then since this cluster is so phase mixed, the stars could be pretty much anywhere allowed to it by its constants of motion. And so then, yeah, when you look at it in projection, you kind of see that shell-like shape. So for that, you need something that's more internal, such that in the past 5 billion years, the cluster has been able to mix enough such that the stars can move away from the cluster to populate the entire configuration space.
Okay, thank you. So now maybe the supervisor. Paola and Marco.
The supervisor have no questions. No, I mean, it has been, I think, a long journey because it started during COVID, in fact.
Yeah.
In 2020, Salvatore arrived in Paris and he had to lock down. I think he didn't know more or less anyone. And so we started an internship together, I mean, starting work together, and every morning we had a rendezvous on Zoom, talking for a few hours about everything.
Yeah.
And no, it has been a pleasure. I'm really happy to see this presentation today. Yes, you have done a really, really good work, and I'm really happy. And I think that you showed that there is still a lot to do.
Yeah.
So take a break and then keep working on these things.
Yeah. Yeah. Thank you. Thank you.
After the lunch, you can take a break and then.
I'll be back at it this afternoon. Don't worry.
It was a pleasure to work with you, and it was very funny, and we learned a lot of things, and so it was a real pleasure.
I think if I can add, it's always nice when you have the feeling to learn with the student, to learn together. And so I think it has been really enriching for all of us. And thank you.
Thank you. I have to thank you too. Thank you. Thank you so much.
Thank you very much. So now we are going to deliberate.
Okay.
And maybe we'll do that in the room and all the other people can get out for a few minutes. Or maybe I forgot to ask if there is a question from the audience.